Hello everyone and welcome. In this video we are going to prove the law of cosines. So the objective of this video is pretty much self-explanatory. So using this diagram that we have on the right, we're going to prove that a squared is equal to b squared plus c squared minus 2bc times the cosine of a. Now, if you are not familiar with the law of cosines, I will make a video, well, a series of videos about trigonometry, and among them will be a video about the law of cosines and its application. So hopefully, if you watch those in the future, you will get a better understanding of how this proof is going to work. So let's get started. So we're going to use this diagram extensively to build our foundation and a series of equations so that we can solve for the law of cosines. So this triangle ABC is made of two right triangles. We have triangle CAX and triangle CBX. Both are right angled triangles as indicated. And so we can express each side, the sides of each triangle in terms of the Pythagorean theorem. So for triangle CAX, as you can see, h squared plus x squared is equal to b squared. And for triangle CBX, we have h squared plus c minus x whole squared equals to a squared. Now, both of these equations have h squared in common, so which means we can solve for h squared basically, right? So we have h squared is equal to b squared minus x squared for triangle CAX, and for triangle CBX we have h squared is equal to a squared minus c minus x whole squared because we subtracted x squared and c minus x whole squared from the corresponding left-hand sides. So because we have now isolated h squareds, we can basically solve for them. We can set the right-hand sides of both equations equal to each other. So we have b squared minus x squared is equal to a squared minus c minus x whole squared. We can expand c minus x whole squared, keeping in mind that we still keep the negative sign outside the parentheses. So we have b squared minus x squared is equal to a squared minus, in brackets, c squared minus 2xc plus x squared. And you can do that by foiling it using the distributive property, or if you're that clever and want to flex, use the binomial theorem, though it's really not that necessary for this one. And now we can distribute the negative sign into the parentheses. So we have b squared minus x squared is equal to a squared minus c squared plus 2xc, because we multiply the negative 2xc by a negative 1, so negative and a negative gives us a positive. And then we have minus times a plus, which gives us a minus x squared. Now, we can get rid of the negative x squareds, and we can subtract the a squared to the left-hand side and the b squared to the right-hand side. So we have a squared is equal to minus b squared minus c squared plus 2x times c, right? So we subtracted a squared and b squared into the other sides. And now, because we have a negative a squared, and obviously we want a positive a squared for the law of cosines, we just divide everything by negative 1. So we have a squared is equal to b squared plus c squared minus 2x times c. So already we have a crude form of basically what we're looking for. We have an a squared is equal to b squared plus c squared, and then we have minus 2 times something times c. Now here, we need to get rid of the x. We can't have an x in the law of cosines, and somewhere we need to introduce a b and a cosine of a. So how can we do that? So let's look at the diagram. So we need a cosine where we have an x and a b. Well, we have the cosine of a, which is x divided by b, the adjacent over the hypotenuse from our SOH-CAH-TOA. So cosine theta is adjacent over hypotenuse, so it's x divided by b. Now, to get rid of x, what we can do is we can isolate x. So to do that, in this case, we multiply both sides by b, so x is equal to b times the cosine of a, and then we can substitute b cosine of a into the equation for x. So we have a squared is equal to b squared plus c squared minus 2x times c, and then we put in b cosine of a for x. And then if we just rearrange it, we can just reorder the terms a bit, and then we get a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of a. And we put a QED to let you know that we have formally proven the law of cosines. Now, there are just two final things that I'd like to mention about the law of cosines. First of all, unlike the Pythagorean theorem, which only holds true for right-angled triangles, the law of cosines holds true for any triangle, regardless of whether you're talking about a scalene triangle, where none of the sides are equal, whether it's an isosceles triangle, so two sides and hence two opposite angles are congruent, or for an equilateral triangle where all sides, hence all angles, are congruent. The second thing is that you can write the law of cosines to solve for different variables. You can rearrange them in different ways. So far in this video, we have only mentioned it as a squared is equal to b squared plus c squared minus 2bc times the cosine of a. On the other hand, you can rewrite them as in two other ways. So you can say b squared is equal to a squared plus c squared minus 2ac times the cosine of b, and what is, I think, my personal favorite, c squared is equal to a squared plus b squared minus 2ab times the cosine of c. The third one's just my favorite because it looks the most like the Pythagorean theorem, and that's how we essentially derived the law of cosines from the Pythagorean theorem. So it just looks cool. The final thing to note, sub-point basically, is that where you have the side squared on one side, you must have the cosine of the corresponding opposite angle on the other side. Now let's just unpack that slightly. So on the left-hand sides, you see a squared, b squared, and c squared. The little a's are the little letters, the small letters in geometry are always the sides. The capital letters are either the vertices, or the angles. So a squared is the side squared, and the cosine of capital A is the cosine of angle A, and angle A is opposite to the side A. And the same thing applies for the rest of the two variations of the law of cosines. So with that, I think we can conclude this video. I hope you enjoyed it. Thank you very much for watching. Please subscribe to check out to be notified for other content. And with that, thanks for watching. Goodbye.